This question is about diffraction grating from October-November 2018, paper 22, question 5. Red light of wavelength 640 nanometer is incident normally on a diffraction grating having a line spacing of 1.7 times 10 to the minus 6 meter as shown in the figure 5.1. The second order diffraction maximum of the light is an angle theta to the direction of the incident light. Show that angle is 49 degrees. Before answering this question, I'm going to bring back your notes. This screen, which is called diffraction grating, has many lines or slits. As the light passes through all these slits, right here, is going to diffract. And because all this light on the other side are coherent, is going to recombine, creating areas of constructive and destructive interference. Then a steady pattern is going to be formed on the other side of the screen. So now we have, for example, this here, which shows a wavelength that is very small, that corresponds to the wavelength of a blue light. Then in other sections is going to create a wavelength here, a little bit bigger, longer, that corresponds to a red light. A simplified diagram can be explained this way. So here we have different colors of light depending on the size of the wavelength that is going to be formed after diffraction. If it's a white light passing through this slit, we should see the color going from blue, green, yellow, orange, and red. Here is a colorful diagram to indicate when the white light passes through a diffraction grating, is going to show the pattern of colors with the same sequence from violet to red. At the bottom from violet to red, and here in the center there will not observe any color, and here is called zero order. Now it's important to notice the red color is the one that bends the most, and the violet bluish shade bends the least. It's also important to notice the angle the violet and bluish shade make with the zero order is smaller than the angle the red-orange shade makes with the zero order. So here is the angle the ray makes with the zero order. So this is one, this. As the color starts to bend more, so then the angle starts to increase. So whatever our analysis go to the upper section of the zero order, the same goes for the lower section. So if the incident light is white, it's going to produce on this screen different colors. But if the incident light is a single color, like red or green, is going to produce here the same color of the single light here. But in this case, white light is going to break down into its components from red to violet. In this particular problem, the incident light is a single color, which is red. So we should be expecting here on this side just red dots, and it's going to be identified as order. So here zero order, the the dot will be more pronounced, brighter. And the first order, not as bright as this one, for the same reason that we studied before. The wavelength is going to arrive here with a phase difference 0. So which means that there will be only constructive interference, so that's why it will be brighter. So I place some red dots here to illustrate that the 0 order, the dot or the circle is brighter than the other ones, and it's bigger too. So just like a double slit diffraction, we have a formula for diffraction grating. We also have a formula that relates all the variables involved here. The first variable is the order number, which is represented by the letter N. Then the wavelength of the light is equal to the distance between slits in this screen times the sine of the angle a particular order makes with the 0 order. Because this first question, want to verify that's the angle, I'm going to rearrange this formula in terms of the sine of this angle. Now, I'm going to do my substitution. So N, the problem states that is the second order diffraction. So N is 2. The wavelength was provided 640 nano. So nano, we are going to use the multiplier 10 to the minus 9. Over D is the line spacing that was provided, which is 1.7 times 10 to the minus 6, right here. Calculator. So 2 times 640 EE negative 9 is equal, divided by 1.7 EE negative 6 equal, and we want the inverse of a sine of this value. So this is going to be inverse of a sine. So inverse of a sine of this is 48.84, which is approximately 49 degrees. So here we conclude the angle is correct. The second question, determine a different wavelength of visible light. Notice that is highlighted here, visible light, that will also produce a diffraction maximum at an angle of 49 degrees. These diagrams illustrate this story. So here we have what we know from our original problem. The red light of 640 nanometer is going to produce a maximum diffraction at second order of 49 degrees. Now, we have another light that we don't know that is going to produce also a diffractional maxima with this value, but we cannot state that will be also at the second order because we have two different lights here and they bend differently. One thing that we must consider is the N, which is the order number, must be a whole number. In both cases, the formula is the same. Now, with this blue ink, I'm showing the next step of my formula substitution. So in this case, my N is 2, my wavelength is 640 nanometer. The D and the data was provided, but is the same of this one. So D, which is the lines spacing on the diffraction grating, didn't change, is the same. And the angle is also the same. So we can use this information right here because both are equal. So we can make these two sides two sides of the equation also equal, all right? So this is equal to this, and this is equal to this. They are the same. So we can state that 2 times 640 nanometer is equal to n lambda. So this is this step. So this is equal to this because these two are equal. Okay, so I'm going to rearrange this formula in terms of lambda. So lambda is this wavelength of a visible light that I want to figure out is 2 times 640 nanometer over n. Great, but I don't know who is n. Well, I know n in this case is not going to be 2 and must be a whole number. Let me try 3 and see what happens. So then I have here lambda is 2 times 640 nanometer over 3. So 2 times 640 equal divided by 3. So the result of the calculation is approximately 426 nanometer. However, is asking in meter, not in nanometer. So we have to make some work here. So the question is, which color is this? 426 or almost 430 nanometers. So if you will look the visible light spectrum in terms of the wavelength in nanometer, so this visible light is right here at the range of violet and bluish. And the light from the problem, the 640 nanometer, is right here in this range of reddish. So I think the assumption of n is 3 works because led me to actually a visible color of light. So now we just need to convert 426 nanometer into meter. So right here is showing, I make the divider here. So my calculation is 426 nanometer, and my job now is convert to meter. And what I'm gonna do is the 426 is the same as 4.26 times 10 to 2, right? To the second power, times nano 10 to the minus 9. So this is 4.26 times 10 to the minus 7 meter. And the mark scheme shows the final result as 4.3 times 10 to the minus 7 meter. So that is the answer, the official answer for this problem.